objects, this thing is driving me crazy. These are the elliptical galaxies, and the red points are what we call classical bulges. So this is a bit technical, but for the non-specialist, just consider bulges come in two types. We now know that spiral galaxies have two types of bulges. One we call classical bulges, one we call pseudo-bulges. This is John's terminology. Classical bulges, you can think of them as basically little elliptical galaxies. They are red and dead, and they formed most likely at high redshifts, and most likely very quickly on a short time scale, and most likely with very high dissipation, okay? Lots of gas. Either doing major mergers, gas-rich mergers, or doing cold flows, but they form over a quick time scale, in a quick starburst, almost one-time burst. Okay, so these are basically objects that form very early on in the universe, again, through gas-rich processes. And if you isolate just these classical bulges and elliptical galaxies, they form this very tight sequence. However, if you include these so-called pseudo-bulges, these blue points, okay, these are objects where the bulge has formed over very long time scales, mostly through internal, what we call secular processes, by gas dissipation driven by bars, by spiral arms, by minor mergers, okay, not by these violent quick events. These blue points, you can see, do not follow anything. Okay, the scatter is much larger. It appears to be some 0-point offset if you dare to, in fact, call it a correlation. But clearly, this population of blue points is very different than the other points. That's the key. Okay, so it's not true that these fundamental correlations are independent of galaxy type. In fact, they're strongly dependent on galaxy type. And this is a major clue. Again, these red points and black points were formed very long ago, when the universe was, redshift of 2. Okay, that's when elliptical galaxies were formed. These things are still forming stars today. Okay, so this is two characteristically different modes of galaxy growth, and apparently also different modes of black hole growth. Going back to this infamous M-sigma relation, the slope is still 4, well, a little bit larger than 4. The intrinsic scatter is just less than 0.3 dex. The more dramatic revision comes from looking at the correlation between black hole mass and bulge mass. Okay, remember the so-called Magorian relation. And there are 3 things to note. First, the slope is formally, although marginally, steeper than unity. It's not 1, it's closer to 1.2. The normalization is not 0.15 or 0.13, but it's really about 0.5. This is a significant increase by about a factor of 4. Okay. The relative mass fraction of the black hole compared to the bulge is 4 times higher than what we thought. And the intrinsic scatter is not larger. In fact, it's the same. And because this relation is nonlinear, in fact, this mass fraction is not uniform. Okay, so here's the old value. This is the new value, but it's not constant with mass. In fact, this is a slow, weak function of mass. Let me switch gears and get back to this diagram that I started the talk with to address another extremely interesting but related problem. Back in 1998, we were very confident in this. So we had this fancy NASA press release, this beautiful graphic, and we said, what happens when you have no bulge? Well, we said no black hole. In fact, we put in a NASA press release. Okay, we were so confident we put in a press release. That's because every bulge that we looked at had a black hole. And we thought that if there's no bulge, there should be no black hole. That was a mistake. What we did not show was that every black hole had to have a bulge. That's a different question. Okay? We did not show that every black hole must have a bulge. This is not just a little minor detail, because this is extremely important, because back when the universe was young, when galaxies first assembled, probably there were many galaxies that were just disks, so had no mature bulges. The question is, So this bears on the question of what were the original population of seeds that ultimately grew to become the supermassive things that power quasars. What is the first generation of galaxies? What is the first generation of collapsed objects that could be the analogs of the seeds of supermassive black holes? And is there any way to see them in the local universe? Okay? And is the bulge a necessary condition to form a central black hole? So these are very basic questions that we'd like to know. And it's been challenging to do this observationally because even with the power of HST, with a resolution of 0.1 arcsecond, it is not possible to have enough resolution to resolve the so-called sphere of influence of the black hole. That is a physical scale you must probe, right? In order to be able for the scale smaller than which that the gravitational potential of the black hole dominates instead of the gravitational potential of the stars around it. And for a 10 to the 5 solar mass black hole, basically, you cannot do this beyond the local group. Okay, so for more than a decade and a half, the only example we had was this neighbor, which is M33, okay? And we knew the answer. The answer is M33 in our backyard has no black hole more massive than 1,500 solar masses, a very stringent upper limit. And that is the only solid dynamical evidence that we had. Beyond that, we have to turn to globular clusters. So this is M31 Andromeda, this is M32. And out here, you can hardly see it, but this is the most luminous, most massive globular cluster known, at least in the local group, okay? It has a name called G1. We treated it as if it were a little galaxy by getting very deep HST observations and very deep Keck observations. And we found that, in fact, it has a massive central object that's dark, has a mass of about 20,000 solar masses. But that's it. That's all the evidence that we have. And that's all the evidence we still have. This is a problem for the GMT, for the TMT, the next generation 30-meter telescope, where the diffraction limit would be 10 times that of HST. So you can do this for larger samples of objects out to 10, 20 megaparsecs. You can go to Virgo, okay? But this problem is really pressing because in the meantime, the Sloan people have been finding all these high redshift quasars, okay? 5.5, 6, and now 7. And they already had black hole masses of billions, 10 billion solar masses. Okay? So what was the first generation? What were the very earliest seeds that grew through these things? Okay? And for people interested in reionization, what role did these early generation of small black holes have on the epoch of reionization? Well, if you ask the theorists, they tell you, well, it's easy. You can form from the pristine metal-free gas. It's very easy to make these, massive stars, these population 3 stars, because there's no cooling, so there's no fragmentation. So you can make these 1,000 solar mass stars that can produce black holes of hundreds of solar masses, okay? Other people would tell you that, okay, you can just collapse 10 to the 5, 10 to the 6 solar mass clouds directly to form, all of it just goes into forming these massive black holes. There's no problem at all. Theoretically, again, when the universe is so simple, you can use your imagination and do this, especially in a computer. Okay. But I'm an empirical observer, and this is not satisfying. So I turn back to the local universe. This is always my benchmark. And I did a simple thought experiment. If such a population of low-mass black holes existed, the best chance to finding them would be to look at the simplest, lowest mass galaxies. Can we find, by focusing on the Hubble sequence, way here, not these big things, but the smallest things, okay? Is there any way to find little quasars? These galaxies, even though they have survived for Hubble time, we know that they are, very simple, undeveloped galaxies. That's obvious. These are simple, low-density disks. They've never had any interactions. They've never had any mergers. Otherwise, you can just destroy them. Right? They're very fragile. Okay, so they're the lone survivors. They were not formed today. They were formed a long time ago. We know that from the stars. They're very old. There's some star formation, but most of the stars are actually very old. Okay, they started forming a long time ago, but they survived the chaos of the hierarchical merging. Okay, and if there are any tiny black holes, they ought to be in here. But I cannot find them by resolving the sphere of influence with HST, and I cannot wait for the TMT or GMT. So let's use a cheat, okay? And let's simply look for AGNs, active galactic nuclei. Let's just search for little quasars, the way we know how to search for AGNs, because to the extent that AGNs and quasars are powered by black holes, even if I don't have a very precise measurement of the mass, at least I know which galaxies have them and which galaxies do not have them. That's a very important first step. And I knew this could be successful because back in my PhD thesis long ago, I had discovered two such objects, okay, along with Alex Filipenko and later with my classmate Aaron Barth, okay? And these are two examples. These are very local objects, and maybe this doesn't mean a lot to you, but for the spectroscopists or people who've ever looked at quasar spectra, you would recognize immediately that they have the spectroscopic fingerprint of quasars. Okay? And specifically, in addition to the technicalities of the line ratios and all of that, the most telltale sign is these broad features. Okay? This fast-moving gas I told you about, what we call the broad line region. That's what astronomers call the broad line region. Okay? It comes from material very close, deep in the gravitational potential. These objects also have them. Okay? But if you look at the galaxies, they look nothing like the galaxies that host quasars. This is NGC 4395, and it's exactly one of these tenuous, very, very fragile, undeveloped galaxies. In fact, it has no bulge whatsoever. There's absolutely no bulge. There's a little nucleus, that's where the little quasar is, but there's absolutely no bulge. This is as pristine and as juvenile a galaxy as it comes. Okay? It's only 4 megaparsecs away, basically in our backyard. And it has a black hole mass, I don't have time to describe the details, in the range of 10 to the 4 to 10 to the 5 solar masses. That is, it's 1,000 times to 1,000,000 times lighter than the most massive black holes that we know. Remember, they can reach a few times 10 to the 10 solar masses. The other object that I showed is this guy, which is even more remarkable. A tiny little dwarf galaxy. No disk whatsoever. It's just a tiny little galaxy. And it has a mass of 10 to the 5. Okay? So in the entire history of astronomy, up until then, we knew 2 objects. But that's very important. This is a proof of concept that nature can make it. Nature can make this type of object, and they can make it in these very interesting environments that clearly are not bulges. These are clearly very, very primitive galaxies. But how do you find more to build statistics in order to turn this into a scientific problem? Well, instead of looking at hundreds of galaxies, you need to look at hundreds of thousands of galaxies, 1,000,000 galaxies. So the Sloan Digital Sky Survey gave us a gift. And Paul Ho and Harvard gave me another gift named Jenny Green. Jenny Green is a graduate student at the time, came over to Carnegie, and in a very short period of time, wrote a paper that basically changed the field and got her professorship at Princeton. She quantified the entire mass function of supermassive black holes in the local universe, the 9,000 objects with redshifts less than 0.3. And we were interested in a very narrow question, which is, how many low-mass black holes are there? Well, out of 600,000 galaxies, we found 200. We redid the exercise later and found another 100, so 2 to 300. Very, very tiny fraction. But nonetheless, it's 1 order of magnitude more than we had before. And this has basically sparked an industry, the 6 international conferences that have been held since that time. Why? I should remind you, because these tiny little black holes, When they merge with bigger black holes, you create very unequal pairs. And the in-spiral of these highly unequal pairs should produce gravitational radiation in a range that is detectable. Okay? It should have been detectable by LISA if they had not canceled it. But now the best hope is with pulsar timing arrays. So the gravitational wave community is extremely excited because this is precisely what should dominate the extragalactic gravitational wave background. But from an astrophysics point of view, we're just interested in where do they live, what kind of galaxies are they, and we've done a very exhaustive HST survey. Out of all of these objects which we've imaged uniformly with HST, only one object out of 200 has a bulge. This is it. It's a big bulge, a classical bulge. Okay? 2/3 of them look like this. Hardly any bulge, and if there is, it's what we call pseudo-bulges. They're not real bulges, they're little things that are still forming. And 1/3 of them are these tiny little dwarf galaxies. Okay, so we've generalized this problem from 2 to now a significant sample, and it's very interesting for all sorts of other reasons. You can study super Eddington accretion, you can study all sorts of AGN-related things. Let me conclude by mentioning another application. So what I did not say, how do we manage to do this? How do we manage to estimate black hole masses? Okay, for this type of audience, I didn't go into the technical details. The reality is over the last 10 years, since the dynamical detection of black holes in inactive galaxies, we've developed secondary techniques and tertiary techniques to extend the black hole mass estimation to active galaxies, to quasars, to things with broad emission lines. Okay, the technical terms are reverberation mapping that you may have heard about. Okay? But for this audience, I won't belabor the point. The point is that we've calibrated techniques using the width of the emission lines, which is a measure of the virial velocities, and we've devised methods to estimate the size of the region and combine them to produce essentially the virial product, okay, RV squared, to obtain masses, which we've calibrated, and we can obtain masses with accuracies of about a factor of 2 to 3. And we applied it to these little objects, and we and others have applied it to really big objects. These are the most massive black holes at the highest redshifts. Okay, so now what I'm shown here in blue is a sample of high redshift quasars, in redshifts 2, 3, 4, 5, and even 7, that have black hole masses estimated in this way. So they're not very accurate. They have uncertainties of factors of 2 to 3, okay, random uncertainties. And amazingly, many of these objects, not only do we know roughly the black hole mass, we now have some constraints on the property of the galaxy. Now, this is really a cheat. I don't know if it's a bulge, okay? It's a galaxy. You can see the host galaxy either with HST, by looking at the stars, by kinematics of various types. The radio astronomers have helped by measuring emission lines due to CO, due to C+. Okay, these are radio emission lines. The point is that we have some way of estimating the virial velocity, the gravitational potential of the host galaxy, and we can put it on this common plane. And what astounded me when I did this about a year ago is that there is any correlation at all. You shouldn't be impressed that it's tight, and I do not expect it to be tight. In fact, I have no idea what the error bars are. But whatever they are, they're huge. So the intrinsic scatter must be much less than this. Okay, this is a factor of 2 or 3 or even 4, and here I have no idea. Okay, whatever it is, that should, crop it up. Okay, the fact is we see something, and it's roughly of the same form as we see at redshift 0, which is this dashed line. But it's all systematically above the dashed line. So at the highest redshift, when the universe was only, 1 billion years old, or 2, okay? The mass of the black hole was significantly higher than the mass of the galaxy compared to the local normalization. This is for quasars that have already shown their glory. These are unobscured quasars shining. These are not the growing things. These are things already have blown out of their cocoon. They've already emerged out of their dusty environment. However, if you look at quasars that are still deeply buried in their gas-rich, dust-rich environments, what astronomers and radio astronomers, like Wei Hao, calls SMGs, sub-millimeter galaxies. Okay, this is what the SMA does. Okay, these are the red points and some of the yellow points. There's two remarkable facts. First, they already have a lot of mass. In fact, the star is already 10 to the 11 something solar masses. They're still forming stars like crazy, but they already formed a lot of mass. In fact, almost as much as they'll ever form. The biggest elliptical galaxies don't go much beyond this. So they've already grown like crazy. But the mass of the black hole, however inaccurate it may be, is all the way down here. It's lower by factors of 10 or 100 compared to the blue points. In other words, the galaxies that are actively forming stars, apparently the black hole growth is lagged behind significantly. It is not true that the black hole and the galaxy grow in sync, in a tightly synchronized manner, like I described in that movie I showed you. Okay? It's not true that energy feedback tightly couples and controls both processes to keep them on some kind of relation. It does this and it does that. That's one important result. However, what I'm wondering about is, even if this is the case, how does it know to stop there? Why doesn't it go all the way up there? And why doesn't it stop down here? So somehow there's a ceiling, it knows when to stop. So there is some type of controlling mechanism, some kind of feedback, but it's not synchronized in the way that is depicted in those simplistic feedback models and simulations that are very, very popular. Okay, this I can tell you, okay? And as I mentioned, it is true that these objects are way above the normal local normalization, okay? By as much as a factor of 10, people have claimed. They're the highest redshifts. These are already the most massive black holes. In fact, they're not going to grow much beyond that. Below redshift of 2, the black hole mass might increase by 30%, 50%, but it's not going to double. So the black holes basically have done all the growing they're going to get. But the galaxy, in order for them to converge to the local line, they have to increase by a factor of 10 or 5 or some large factor, okay? How in the world do you do that? How do you increase the stellar mass by a factor of 5 or 10? In fact, it's impossible. If you talk to the galaxy formation people, massive galaxies do not increase their masses by an order of magnitude since redshift 2. Well, this was an optical illusion. That's because they were using the wrong normalization. If you use the latest normalization, remember, latest normalization is higher by a factor of 4. This is the black line. Okay? Now it's better. Now all you need is to increase the galaxy mass by a factor of 2 to 3. Okay? So it's still true that the black holes have already built most of its mass. And the galaxy still needs to catch up by about a factor of 2 to 3. But that's okay. This is a highly technical conclusion, which most of you may not fully appreciate, but it's actually okay. The galaxy formation people, in fact, tell us that the most massive elliptical galaxies, for those of you who know the jargon, the red nuggets, in fact, double in mass, triple in mass since this epoch. Okay? And that's exactly what you need to put it from the green line to the red, to the solid black line. Problem is solved. Okay, so these are the recent updates. We've extended the mass function of black holes down by 2 orders of magnitude to about 10 to the 4. Other people have extended up by a factor of 10. So now the black hole mass function goes at least from 10 to the 4 to 10 to the 10. It continues to be true that all bulges contain black holes, but it's not true that all black holes contain bulges. We've discovered hundreds of galaxies that contain black holes in the mass range of 10 to the 4 to 10 to the 6, but they do not live in bulges. These are Bulges galaxies. The correlation between black hole mass and bulge mass is marginally steeper than unity, and the mass fraction has roughly quadrupled. Instead of 0.15, it's more like 0.5. The M-sigma relation is roughly the same. It's a little marginally steeper. A very important conclusion is that it is not true that the M-sigma relation is more fundamental than the MM relation. Why do I keep harping on that? It's because literally there are 500 theoretical papers that have been written to explain this by really smart people. Okay, it's not true, it just isn't. However, these relations are tight only for these old classical bulges, elliptical galaxies. They're only for this subset of galaxies that were formed a long time ago. So whatever it is that said it happened a long time ago. Back when quasars were doing their thing, and we see it. I just showed you these high redshift quasars. They define this nascent, this scaling relation already at the highest redshifts. The scatter looks larger. I have no idea if it's how much larger because I don't have error bars, but it certainly seems to be there. Okay. There is evolution in the scaling relation, but it's very mild. It is not this dramatic factor of 10. Okay, it's really just a factor 2 to 3, which is entirely explainable by current understanding of galaxy evolution, because the massive galaxies will double in mass. And if AGN feedback works at all, if it works at all, it only works for this subset of galaxies, again, at very, very high redshifts. So these are the major conclusions in our review. And let me end by advertising the Kavli Institute for Astronomy and Astrophysics. This is a very new institute that's only been established formally 7 years ago. The first director was Doug Lin. It's built on a beautiful part of Beida. Okay? It actually looks like this. In fact, just this week, they started putting water. This is what the university president actually promised me, but I think it's fortuitous. Okay, but we're going to have a lake. In fact, the lake is beautiful. It's really beautiful. It's a beautiful building, very nice environment. We are 1 order of magnitude smaller than ASIAA, but I've since combined the Department of Astronomy, the active faculty, with the KIA faculty. We have 22 faculty spanning theory and observations. They're very active, very deep and very diverse faculty, working in many areas of astronomy. The emphasis is going to be on galaxy formation, the ISM, exoplanets, and numerical simulations. And just this week, we released a brand new webpage, which I welcome you to visit. There are many new features to introduce you to the Institute. And if you're ever in Beijing or just in China, I welcome all of you to come by and visit. So thank you very, very much.
Any questions?
I will ask something as a physicist. Dark matter, dark energy, does it matter in all of those things which you showed here?
No.
Where it is hidden, if it is?
Dark matter, of course, exists in galaxies, and they dominate the total gravitational potential of a galaxy by about a factor of 10s to 100. But it's on a very different scale. They dominate in large scales. So what we're talking about here is basically what's happening at the absolute central scale. And the density profile of dark matter halos is such that it's not really that, it's not totally negligible. And the latest dynamical models that fit the kinematics do include the dark matter halo. It's really a small perturbation. And dark energy, no. I mean, only to the extent that it affects the larger scale distribution.